Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL certification course on architectural acoustics. Today we are in the 7th week and this lecture number is 34. This is the 4th lecture on the 7th week of this program of architectural acoustics, and today we will discuss about the structure bound sound transmission in general. This as you remember, in the lecture number 31, 32 and 33 are on the airborne sound. 34 and 35 is on the it will be on the topic of these two, or will be on the 34, and the 35 is structure bound sound. So, the learning objectives are we will develop a kind of the fundamental understanding of the structure bound sound, transmission of the structure bound sound, and also we will going to explain what are the different parameters that actually influence the structure bound sound transmission. The structure bound sound by definition is, as we already discussed in the lecture 31, is there are two ways a sound propagate from one place to another. One through the air, which is the airborne sound transmission, and for that we need to develop some kind of a transmission loss. Suppose from source room to the receiver room some sound is propagating. So, the transmission loss of the in between partition wall is one of the important criteria, whereas the structure bound sound are propagating through various due to some kind of the vibration or some kind of various impact, and that will actually propagate through some of the structural members, and some of the structural members which is embedded into a building system. Those structural members are suppose a floor, suppose a beam, column, or maybe a slab, or maybe some kind of metallic pipelines, some duct, all those. So, we will try to see what are the ways it is propagate and how we can control this particular vibration, and that is a mechanical vibration of course, but this mechanical vibration propagates the sound from one place to another. And from your basic physics you must know that the velocity of the sound in solid is much faster with compared to the air. So, that is another issue. So, the what are the different source of the structure bound sound in a building? Let us see one after another. The first one is some kind of a pump. Pump is a integral part of any the building or maybe a building complex. It may be some kind of a reciprocating pump or centrifugal pump. There are compressors for the cooling towers or for the air handling units for air conditioning system. There are electrical motors and generators are another part of a particular building or particular site where there are a group of buildings. Yes, there are workshops are there also a part of industrial building or maybe some kind of the institutional building. The workshop is one of the common criteria, the space criteria, and then there are some kind of machines and the shop machines and all. So, that also creates some kind of a vibration or some kind of structural bound sound, and moving machines like elevator, gantry girders also are some of the sources of the structure bound sound. Now, what are the effect of this structure bound sound? So, I have categorized the structure bound sound or this vibration effect into two the broad category. One is the structural effect, which is actually because of some kind of differential settlement may occur because of the vibration. There may be some kind of a crack which is existing in a building because of the vibration. This crack will be initially maybe hairline crack, that may be widened or maybe that may be elongated, or there are some kind of a fatigue load. Fatigue load is something like a reversible kind of a load applied in a particular structural member that creates some kind of a serviceability problem. But we are interested to know about the acoustical effect of the structural bound sound, which is actually a kind of annoying kind of a noise in a occupant, because the structure bound sound vibration has a typical frequency band, and that is sometimes very boring in that sense, and it created some kind of a the negative sensation in the human brain. So, that has to be stopped, that has to be actually eliminated from the from source room to the receiver's area. The noise may be interfaced with some kind of a precision instrument or so. Suppose there are some kind of the instrument in a high tech laboratory, where a particular measurement is taken for some kind of the nano or the atomic range measurements or so. So, those kind of structure bound vibration or noise may hamper that particular reading, or so there may be some error involved in that particular the output in from that particular instrument. Structure bound noise also induce lot of the physical problem like headache, some kind of the high blood pressure and the deafness and all those kind of a thing. So, this is one of the area which generally people ignore, but need to be addressed properly by an architect. So, as I understand, or as probably you also understand in this particular structure bound sound regarding that area, it is actually the initiated due to some kind of vibration of a mechanical vibration of a machine. So, this vibration has to be isolated, and there are different techniques, and if those techniques is grouped together and again try to classify those two techniques, there are two such classification. The first classification is called the active vibration isolation. In active vibration isolation, architects may not have a role to play. It has kind of a area which a mechanical engineer or maybe the electrical or electronics engineer may have a much more the role to play over there. What is that? That is nothing but the modification has to be made in the vibration control by virtue of some kind of a amplitude modification, vibration amplitude modification. So, as you know, the amplitude is if it is a high amplitude, is having a the power of the emission is much more. So, if you can modify that, or if you can reduce that particular the amplitude, then probably the vibration, the effect of the vibration will be less. So, the control of the machine, the effective utilization of the some of the component of the machines or the new technology, new development, all those are involved in active vibration isolation. So, it is all about the machine itself, it all about the integral part and the design of the machineries also. So, the architect does not have any role in that, but the second one, which is a passive vibration isolation, yes, we have a much to play, you have a much bigger role to play. In that, the vibration is isolated from the vibration machine during the propagation stage. So, a architect will definitely not going to touch the machines and the machinery part, but he has to actually think about how this particular propagation will be minimized from source room to the receiving room by virtue of some changes in the building configuration, some structural configuration of the buildings and all other. So, here let us see the what are the different way, and let us see find out from the vibration identify the problem of this propagation and the passive isolation. So, here we have a path system where a source is there and a receiver is there, and in between the source and receiver there is a path. So, these three areas we can actually touch and actually control. So, the first one is the source, the mechanical vibration of the source of the structural vibration is by a mechanical vibration or any kind of a fluid flow disturbance that may generate in the machines or may be generated in the some part of the machines, and while it is propagating. Suppose if you take a pipeline, suppose if you take a building pipeline where the water is flowing or the wastewater is flowing, that vibration or that kind of the structure bound noise is because of the disturbance in the fluid flow. If there is a laminar flow, it will be much less, the much less amount of vibration will produce and your control will be much easier. Whereas, if there is a turbulency in this particular path of the fluid, the amount of vibration also will be high and your amount of effort to control that vibration is also going to be heavy. So, that is one, and fluid flow may not be always going to be the fluid flow like the water or any kind of a fluid, it may be the air flow also. Sometimes in the building is centrally air conditioned, and from that point of view the air, the cooled air or the returned air comes from through the ducts, and also there are also sometimes disturbance, and there is a fluctuations of the pressure, there are eddies and all those, and the disturbance and this kind of the laminarity of the flows and all will create lot of vibration problem. Next is the path. Path is the structure bound sound or maybe a airborne sound has a kind of a path. It sometimes it is through the structure and sometimes it is through the structure plus the air. So, this path has to be taken into account. So, how it is actually moving from the source to the receiver. And finally, this is a response system where a particular area or a designated noise sensitive zone is marked, and I am going to isolate that particular receiver area from the source of or the path of that particular vibration. So, there are some solutions has been shorted or solutions has been thought of. The first kind of solutions are the relocation of the machines and the foundation system in a rigid kind of a system can be thought of to control over the vibration. There are replacement of the machines or the part of the machines, that is another issue. This is all about the source. Source is has to taken into the consideration, because that if you minimize the vibration from the source, your it is a great duty, great job. I mean, in that way it is a kind of the reduced your propagation of the structure bound sound in a great way. Sometimes we can change the operating frequency of the machines, or sometimes we can change the natural frequency of the machines also to reduce the impact of the vibration or the propagation of the structure bound sound. Next is we can have some kind of a solution from vibration solution from the path. So, we can actually think of some kind of a system where the spring and some kind of inertia block is placed on the machines. So, while it is vibrating, it may vibrate, the source may vibrate its own, but while it is going to I mean taking a path through some kind of a the structural element in a building. So, it will initially it will be taken kind of some kind of a filter off. So, with that particular spring or some kind of a inertia block. So, there are some kind of mechanism happen, and because of that particular mechanism there will be some amount of energy is actually absorbed. We can also think of some kind of a discontinuity in the structural member to just stop the propagation of the sound in the path. Finally, the receiver. So, adding some kind of a damping in the receiving zone is always going to be beneficial, it is always going to be minimize the effect of vibration. We can isolate the receiver from the propagation path with some kind of the making some kind of a special arrangement where it can actually not entertain any kind of a outside vibrations or so. So, we will go in one by one on all the details. The first one, as I told, that the source has to be taken very carefully. So, the position and the placement of the source is very important. Any vibrating machine should be placed in the ground floor. That is one of the important criteria. But why? Suppose a machine is vibrating machine is in the top floor or in the not in the ground floor, then because of the placement and this because of the placement of the machine in the first floor or maybe some other floor, it is actually lose some kind of the stiffness, because if it is in the ground, then it has a wide variety of the support system, because the ground below the ground floor there are there are some soil or there are some kind of a solid base and continuity in the base is available, which add a kind of a stiffening to this particular ground floor. So, automatically the vibration will be stopped or vibration will not going to be propagate from that particular machine to the other component. Of course, it will propagate, but not in a form that it actually the way it propagate in the upper floors also. The next one is that the vibrating machine should not be placed in the center of the slab. I mean, if at all you want to place it in a in upper floors, because many a times we cannot avoid that particular vibrating machine to be, suppose the AHUs and all, each and every floor you have to give some kind of AHUs and which is having some kind of a pump or some kind of a the diffuser. So, those has to be in the different floor, but if it is also placed in the upper floors, it should not be exactly in the central span of the slab, because the center span of the slab is having less stiffness. It should be either the very corner where there is a beam, or maybe another corner where there is a beam or columns are available, is surrounded by at least the two side or at least one side. Because of this beam column association in a particular area, and if you place the vibrating machine near to that, the added stiffness made by this beam and column will give you some kind of a the reduction in the propagation of the vibration. So, next is the structural discontinuity. This is one of the easiest way to control about the vibration propagation. The structural discontinuity, suppose there is a workshop and there is a classroom or maybe some kind of a office. It is a very common the space arrangement in any the college or maybe in engineering college also. There is a workshop and there is a classroom or maybe some kind of a the noise sensitive area. We can provide a structural discontinuity in a form of construction or expansion joint, and definitely the noise will not, vibration noise will not going to propagate, because there is a discontinuity also. We can do it in this, particularly in the railway track and the platform, maybe in the metro railway or maybe any kind of the urban areas where there is a railway track and a particular the platform, and associated with that there are some office buildings and some kind of a the noise sensitive zones are there. So, we can introduce a gap over here, structural discontinuity, and we can actually fill this structural discontinuity some kind of a flexible material of packing, like the felt or the asphalt or those kind of a, or maybe the rubber or maybe the cork sheet, those kind of a material through in this gap. So, structural discontinuity is also going to help us to minimize the propagation of the sound. The next one is the mounting operation. This mounting operation is also wonderful, because this mounting operation is almost essential to take in to stop the to reduce the vibration isolation, to reduce the vibration propagation as such. What happened is that a machine is actually placed over an inertia block or heavy mount block by concrete or maybe the brick machinery, and this heavy mount will be after that, and if you just put it in some kind of a anchor bolt and all the rigidly fixed with this particular inertia block, this inertia block plus this machine will now act as a unit system, as a integral system, and the vibration of that particular machine will be reduced down. So, sometimes we can also provide some kind of a spring, the steel spring or some kind of a the steel pads or metallic pads, metallic strips or flexible pads kind of a thing below the machines, which will again going to arrest, which will again going to absorb some amount of vibration, and the propagation through this red color slab will be minimized. We can also go for some special design base frame, where a mounting base, a concrete mounting base, this green color, also this top green color is the mounting base, and this is the some kind of the flexible padding, and also a kind of a side springs are also designed carefully with some kind of from the vibration equations and all, and it will definitely going to minimize the propagation of the sound, vibration sound or the structure bound sound. So, those are your mounting operations, the types, there are various types, and these are very much adapted in practice. Now, I have two photographs taken from our IIT Kharagpur campus, where one DG set, this is a diesel generator set, is on a inertia block. You see, this is inertia block, which will also help in other way around. It will also lift this particular machine. So, working on that machine will be easier, and also it will sometimes the area may be flooded because of the rainwater also. So, those are the associated the advantage, but basically this is another machine which is the central air conditioning system machine, which is placed again in a classroom complex near to our IIT in our IIT campus, Kharagpur campus, where you see there are this inertia block is having two split. You see there is a black line, that is two split. So, the inertia block is is splitted into two part, the top and bottom, and the central area sandwich area is filled with the felt or the cork sheet layer. So, this is a kind of another arrangement where the mounting or the inertia arrangement with some kind of a special criteria is taken care of. Now, let us see some kind of a fundamentals from the applications and mathematical applications of this the vibration and the vibration isolation. So, as you know from your basic physics is that a mass, a vibration is a basically problem of a mass and stiffness, and a mass of, suppose the object is having a mass m and this is having a kind of a stiffness of k, and then if there is a kind of a force applied on this particular mass, then we can see that there is a rebound or there is a kind of a the resisting force from the spring, which is k into x. K is the stiffness of the system, which is measured in Newton per meter or so, and k x is the displacement. So, if you just multiply k into x, that is the again in force Newton, and which will be actually this force will create some kind of a vibration. A vibration means there is acceleration which is a time bound accelerations or the displacement or so, and this is a sinus, I mean the SHM, that is the simple harmonic motions kind of a thing. So, the force in the body will be m into dx2 dt2. So, that is the acceleration. So, the dx2 dt2, that is your the double differentiation of x with respect to t is also written as the x double dot. So, I can use this particular equation, fundamental equation, as this f minus k x must be equal to this force that exerted in for this mass m into acceleration. And finally, we can use this particular, rearrange this equation like this, and this is the second order differential equation. And this second order differential equation is a solution of in this form, can have a exponential form, and this in the exponential form there is a imaginary roots also, the minus 1 under root. So, and from that we can find out there is a this radical terms, which is under root k by m, is nothing but the circular, the natural frequency of this particular vibrating system, and definitely it will be a circular natural frequency is there, because this particular vibration, motion of the vibration is the sinusoidal kind of thing, or is a kind of a the simple harmonic kind of a thing. So, if I can understand that how this particular k by m comes from this radical terms and exponent, I can now write down the natural frequency of the machine, that is the natural frequency is denoted by f suffix n, which is this omega n, which is the circular frequency, natural circular frequency by 2 pi, and so finally this f n is equal to 1 upon 2 pi under root k by m. Please remember this k has to be the stiffness of the system, which can be expressed in Newton meter, and m is the mass of the system, expressed must be in kg. So, here I have found out a particular f n in the x axis, or I have plotted the f n in the x axis and the operating frequency f o in the y axis. So, what happened is that, suppose a particular machine has its own mass and it have its own the elasticity criteria, and from that elasticity criteria is having a kind of a k. So, if this k and this m is fixed for a particular machine, its natural frequency is fixed. Now, what is operating frequency? When you switch on a electrical cable and the electricity passes through and it starts the machine. So, this machine will vibrate because of the particular operation, and these operations will give you those kind of operating frequency, and this, if the operating frequency and the natural frequency matches with each other, a resonance will create. And what is resonance? It is its amplitude will be high, it will suddenly it will the amplitude will be high, and due to that this resonance effect, the vibration and the noise propagation also will be more. So, that is why I have drawn a 45-degree line, and this red zone, and red line is 45 degree where the f o and f n matches together, and this red zone is the zone where the operating frequency is almost likely matches to the natural frequency, a resonance is created, high rate of structure bound sound transmission will occur. So, our idea will be, we have to actually see the our operating frequency and the natural frequency combination should come in this green zone, either below or maybe above. So, then this resonance will not going to above or not going to occur, this operating frequency and the natural frequency, if this is high or low, a low rate of structure bound sound will be transmitted. So, here what I did is that, suppose the operation frequency of a frequency is 120 hertz and the mass of the machine is this much 15 kg and stiffness is 10 to the power 4 kilonewton meter. So, I can use these fundamental equations for the natural frequency 1 upon 2 pi 10 to the power 4 into 10 to the power 3, because I have to change this kilonewton to Newton by 15. So, 130 hertz is the frequency, that is your natural frequency, and operating frequency is 120 when it is actually going to operate. So, this is very close by and this is in the red zone. So, I need to translate or need to transfer. So, what I did is that I changed the mass, which was actually 15 here, the mass of the machine, and which is rested on the slab itself. Now, I put the heavy mount system, and the mass is now suppose 60 kg, and if it is 60 kg and the stiffness remains unchanged, this f n, that is the natural frequency, become 65 hertz, and now this 130 hertz from here it is moved to the 65 hertz, and the operating frequency remain unchanged 120, and this is your 65. So, the point shifted over here. Why this point shifted over here? Because the additional load of 45 kg I have attached with the particular machine by virtue of the mounting inertia block, and I will reduce the natural frequency, and natural frequency and operating frequency is not matching with each other. The next is what I want to do is that a thin the metal sheet of 0.5 mm thickness and the density of that is 7800 kg per meter square is a part of a machine, and it is having a natural frequency of 1000 hertz. Okay. This is a part of a machine of a particular metal sheet which is vibrating. Now, it is expected to the natural frequency, the operating frequency is also very nearby the 1000 hertz or so. So, and it will definitely create a noise. So, what I want to do, I have to increase the mass of this metal plate by virtue of some kind of a paint over it. Okay. So, I will going to apply some kind of a paint whose density is 1200 kg per meter cube, and I want to find, I want to change the natural frequency from 1000 kilohertz to 900 hertz, and operating frequency remains as 1000 hertz. So, I will be the vibration of this particular metal sheet, which is sometimes vibrating some fan blade or sometimes some kind of a diffuser blade of a AC systems will be minimized, this vibration will be minimized. So, my question is, compute the thickness of the paint, how much thick paint I will apply to increase the mass and decrease the vibration. So, from this equation I can say that the relation between the natural frequencies masses f 1 by f 2 is equal to m 2 by m 1. Now, m 1 is my per square meter mass of the thin sheet, which is 1 into 1 is the area, 0.5 is the thickness of this particular thin sheet, millimeter. 1 by 1000 is this converting this to a meter, and so this is and multiply with the density 3.9 kg is the mass of the sheet, and then I will use this formula, and I want the f 2 as 900 because f 1 with respect to the m 1 is 1000. So, this ratio is 1.22. So, by computing this m 2, that is the new mass of this thin plate should be 4.8, and if it is 4.8, it will give me the natural frequency as 900 hertz. So, I have to increase the mass, it was actually 3.9, but this has to be 4.8. So, 0.9 kg or 900 gram of the mass has to be increased as this particular plate. So, how can I increase the 0.9 kg of the mass? By virtue of some application of some kind of a thick metal paints. So, let us assume the thickness of the paint is T, and the change of mass is 0.9, and again 1 meter by 1 meter and the thickness by 1000, and this is the density of the paint is equal to 900 gram or 0.9 kg. So, if you equate this and solve, you can find out the 0.75 mm thick paint has to be applied over the particular thing. So, if you have the both the sides, so it is one side is 0.75 by 2, another side is 0.75 by 2. So, that way you can apply the paint, and by virtue of the application of the paint will be the mass will increase, and then your definitely your vibration will decrease, and it will be separated out from the operating frequency, and it will not propagate, the resonance will not create. So, this end in this lecture, end of this lecture, let us have take two homework for you. One, first one is the outline the type of passive vibration isolation types of passive vibration isolation technique. So, we have discussed so many techniques. We will also going to discuss some of the techniques in the next lecture. So, let us outline these things, and another question is for you as a homework is that suppose the stiffness of a machine is reduced by half and the mass is get double, then what will be the change in its natural frequency? Is it going to be the same or it will not going to be the same? If it is not going to be the same, it will be high or low, or how many times it will be high or how many times it will be low. That is I am expecting from you. So, that is all for this lecture, and these are the some of the books I have referred for this particular lecture, and thank you very much for hearing that, and we will go to the next lecture in that is the last lecture on this structure bound sound transmission. Thank you.